Donc on va commencer. Hein. Comme je l'ai dit, Erwin connaît très très bien tous ces problèmes de verre de spin depuis des années. Il a fait beaucoup de contributions importantes. Et donc ça m'a paru être vraiment le meilleur orateur possible pour nous parler un peu des aspects mathématiques liés à cette théorie des verres de spin. Je suis très heureux qu'il ait accepté de venir.
Okay. No, I'm sorry that I have to speak in English, so because otherwise I will be blocked. Yeah, okay. The title is a little bit of a plagiarism from Michel Talleyrand. So when Michel Talleyrand had started to work on the mathematics of spin glasses, so I had invited him. I was editor of a probability journal at that time. I had invited him to submit his paper to this PTRF, and then the title of his first paper on the topic was the Sherrington-Kirkpatrick model, a challenge to mathematicians. So I have somehow copied that. Now, there was a lot of progress in the past 30 years so in the mathematical understanding of this parity theory, particularly of the Sherrington-Kirkpatrick models, but also more general models like the p-spin models and a number of other ones. But there are, at least for mathematicians, still a lot of problems with some very natural models in spin glass theory, which are mathematically not very well understood. So here is, okay, this is just a little bit a history of the mathematical understanding of mean field spin glasses, so of course with a personal bias. So one important step was this random energy models. So Bernard had explained, so it's starting, I think, in 85, and then there was Riel's version of it, or Riel's limiting version of it, which appeared in 86. And then Talleyrand started in 98 with a mathematical, there were some other papers also between, but okay, Talleyrand started to work heavily on this cavity method, the rigorous version of the cavity method. So the first papers, okay, for quite some time it was only in the so-called replica symmetric regime. So then, as also was mentioned, Guerra had this replica symmetry breaking bound for the Sherrington-Kirkpatrick model that appeared around shortly after 2000, and then shortly afterwards, actually it took some time until it got published. Talleyrand had the first really mathematically rigorous proof of the parity formula. That was essentially based on techniques he had developed earlier. But for the high temperature regime, he could use it together with this replica bound to give the full proof of the parity formula. Then an important step was also as Derrida had mentioned, that these Ghirlanda-Guerra identities, which were very instrumental and actually the basis of Panchenko's proof of ultrametricity. You see this ultrametricity, which played really an extremely prominent role in the physics literature from the start, was a mathematical open problem even after Talleyrand's proof of the parity formula, because it bypassed this problem. But now, together with this ultrametricity, also Panchenko could give another proof of Talleyrand's result. So now there are two more recent approaches, and actually it's connected with this perceptron. One is based on a Hamilton-Jacobi approach, and this goes very much into differential equations. Jean-Christophe Murat is also a specialist on PDEs, has a program to build the whole mathematical spin glass theory more on this Hamilton-Jacobi approach. I will give, if I have time shortly, I want to explain that. And then there is another approach, a recent approach, and that's for the moment restricted to replica symmetric situations, and which is based on these Thouless-Anderson-Palmer equations. That was invented more or less by me, but independently there was a paper by Yan Ding and Naike Sun, which also used the key idea. So Now I have to repeat something a little bit. Okay, the talk has an overlap with Bernard Derrida's talk. But more a little bit from a mathematical point of view. So okay, I'm just repeating what the Sherrington-Kirkpatrick model is. So I'm okay. This is these inverse temperature parameters divided by square root of n, and then these j's are independent standard Gaussians. You can generalize that. But for the computation, it's easier to take just independent standard Gaussians. And then you also typically sometimes you can forget it, but for some of the aspects, it's actually good to have an external field. So with this h parameter. I'm typically not taking the beta parameter on h here, so I'm just writing it in this way. And these are just, -1 + 1 spin variables. I call this sigma n. That can also be generalized, but already some formulas become considerably more complicated if you replace this spin states -1, 1, say, by a finite states. And then you have the partition function, which is, I'm always taking 2 to the power -n in front in order to avoid the log 2, which is always appearing in the formula. And then, this finite n, mathematicians always call it the free energy. I think in physics language it's the pressure, also minus the pressure. I never know. So. And then, the limit of that exists. That was actually proved before the parity formula was proved. And there is what is called self-averaging. You can take the expectation. So I'm always writing that. So Bernard had written a bar if you're taking the disorder average. I'm always writing it in this way. So you're taking the expectation of that here. And then the limit exists, and the limit is given by this parity formula. So that if you have an external field, it's depending on beta and h here. The parity formula, I've just written it down. So it is the infimum over these parity expressions. This involves this beta and h, and it's it's taking the infimum over it's infimum over probability measures. So you can discretize it. So Bernard always had the measure discretized. But in principle, it's an infimum over say probability measures on the interval 0 to 1. And then this parity expression, I just written it down for completeness. So it's given by an auxiliary function. I have it on the next slide. And then this function, beta square half, and then this integral involving the measure mu. And then I just have to explain what that is. So this object, in mathematical terms, it's true, you can just write it as a solution of a differential equation. So that's I have it here. So it's probably It's not very revealing if you have not seen it. So you're having a function phi, then depending on beta, h, and mu, which are the parameters here, and then it's a function in S, and in S and X are just real variables, and then you have this partial differential equation as it is written here. So this is this parity differential equation, and then you have to take the boundary conditions at 1, which is logarithmus cosinus hyperbolicus, and then you solve it and evaluate it at S. So it's actually known that there's a unique solution of this partial differential equation here. So now an old mathematical open problem, which had just been proved by Offinger and Chen in 2015, is that if you're looking at this variational formula for this parity formula, you are having a unique minimizer. So it's a unique minimizing mu, which is coming from the fact, which is actually rather non-trivial, so that this parity function as a function of mu is a strictly convex function on the set of probability measures on 0, 1. And therefore, you have this minimizer, which is uniquely defined. So the question is, of course, what this minimizer is. Now, even mathematically, this is just analysis problems. So even mathematically, it's quite an open problem. So, for instance, in physics literature, it's always claimed that you have a density part. So at low enough temperature, so at large enough beta. But that's an unproved fact. So that you're having a density part. So. No, mathematically unproved parts, I have to say. Now, if beta is small enough, then actually this policy measure is a one-point measure, and that is what is called this replica. This corresponds to the fact that you have this replica symmetry, as explained by Bernard. So if beta is small enough, then the policy measure is equal to the one-point measure at Q. And suppose this happens up to I have not written it down what the condition is. So it's actually a simple condition. So the Derrida-Saulus line. So mathematically, that's also an open problem. So you see, it's just an analysis problem to prove that the minimizer is at the one-point measure up to the Derrida-Saulus line. There was a lot of work about it, and I think it's nearly proved, but it's not completely proved as a mathematical fact. So. You see, replica symmetry is okay. Everybody is using this expression replica symmetry. But that's coming from this replica computation by Parisi, which the mathematicians don't like. So there are essentially no mathematical results about the validity of this replica computations. All the proofs of mathematical proofs in this theory are more or less based on from ideas of the cavity method. I think Marc Mézard explained last week. Yeah, so. Okay, but okay. In terms of statistical mechanics, it's more or less saying that replica symmetry is equivalent to having a single pure phase, whatever that exactly means, because you're having a mean field model, and then it's not quite clear what a single phase means. But you can make mathematically precise sense of that. But I'm not explaining that. So. Now, a special case, which was actually, I guess, the first mathematically rigorous result in this topic, in this paper by Eisenmann, Leibowitz, and Ruel, is a case if you don't have an external field. Then if beta is small enough, and actually beta small enough is smaller than or equal to 1, which corresponds to this Derrida-Saulus line, but in this case, it's actually proved that it is exactly the correct critical point. So if beta is smaller or equal to 1, then you have just are in this situation, and then you can check that Q equals 0. So the policy measure is just the one-point measure at 0. And then the replica symmetric solution is, and then you can do something which is looks a little bit strange, but namely that the so-called quenched free energy is where you would have this expectation outside the logarithm. You can take the logarithm inside, and prove that then you're getting this beta square over 4. So that was proved in this Eisenmann, Leibowitz, Ruel, but they actually have much more results about it. If you just want to have this result, it's a simple exercise of concentration of measure business. So that's very easy to do. And there's also the paper by Fröhlich-Segalinsky a little bit later. But this was also looking at, in particular, he also had a result of this type. Yes. Now the scandalous fact is that if you're having a simpler model, which I call this bipartite model, is mathematically unsolved to a large extent. So except in high temperatures. So now, I say scandalous. It's actually I'm particularly favorable to that, because when I started to look together with Alain Snitman a long time, long before Parisi formula was proved, we were looking at the Sherrington-Kirkpatrick model, and we didn't make any progress. And then at one moment I said, yeah, but let's just look at this case where you just have the interaction between the first block and the second block. So you see in the Sherrington-Kirkpatrick you're having, of course, all the interactions for all the pairs, but I'm just dividing in two blocks. and then just the interaction from the first block to the second block. This should be simpler. So let's just look at that. So of course we couldn't also not do anything for that. But it's mathematically still a largely unsolved case, this bipartite case here. So now, if people had looked at other forms of the bipartite case where the situation is better, namely, you see here I'm having in the first group of spins, I'm having no self-interaction, and also not in the second. So, but you can also say, okay, let's look at the mixed model where I have, say, a temperature parameter for the interaction, a temperature parameter for the interaction on the first group, and another temperature parameter on the second group. And you have 3 parameters then of this, okay, more general model than that. And for that, depending on the parameters, you can actually mathematically solve it. So I will come to that. So. Now, what you can do is that in this very simple case, you can, of course, just summing out. You see the Hamilton, you're looking at this object where you sum over I, and then you sum with the sigma I, and then you're just having the sigma j's left, and you can just sum over the sigma j's here. So, and then if you're looking at the bipartite case, you only have to sum over the only non-trivial part is you're summing over this sigma 1 up to sigma n half, and then you're having a sum above, which is the sum from say n half to n of just logarithms cosine hyperbolicus coming from this summing out of this sigma j, and then you're having inside this quantity here. So you see this inside this quantity, of course. You see the j's were assumed to be independent. So you see these objects here as a function of j's are independent random variables. But still, this is getting a complicated object to at least to mathematically study them. And then this is a very special case of what people now call the perceptron model. So where you replace this logarithmus cosinus hyperbolicus with an arbitrary function u. So u is just okay on the real axis, and it goes to minus infinity to infinity, including minus infinity. So many a number of interesting cases are just including the possibility to have here minus infinity. And then you're looking at the Hamiltonian, which is just given in the same way as here. You can also take m different from n half. So okay. I'm replacing n half by n, and the first index, the index of j, I'm just taking a capital M here. So and then typically people take m proportional to n. Here it would just be, you see this case would just be that m is equal to n, but you can take other m's. The point is the high temperature regime should correspond to m being relatively small compared with n, so that for instance alpha is small here. But you can have other things, so for instance you can take u smaller. You see the replica symmetric situation should be that either m is small or u is small in some sense here. So. Now, a special case is when this function u is minus infinity, say on the real axis up to a parameter kappa. So here. Now, what you are doing in that case with this partition function is just counting the number of sigmas, such that this, what people call this cavity variable, which appeared here inside the u. So you see, if you're looking at this inside, is bigger than, okay, if you divide by square root of n, is bigger than kappa. So you see, if you have one sigma, you see, if you have one of these objects here, smaller than kappa, then you are catching with the u minus infinity, which in the exponent means that you have 0. And then the whole expression is 0. So this set is just counting the number of sigma. Now, for instance, if you are taking kappa equals 0, you are just counting the number of spin configurations which are in capital M random half spaces of the Euclidean space here. So you're just ending up in that here. So now for this perceptron case, there are essentially mathematically only replica symmetric results for this object typically formulated for small alpha. So there are these celebrated papers by Gardner and Derrida Gardner. So in the 80s, which are based on replica computations here. So like just on a sophisticated replica computation here. So and then there was a paper by Mizar which came to the same conclusion based on cavity arguments here. So then the mathematical proofs first started with works by Talleyrand around 2000 and later. So he needed some conditions on U. So but Talleyrand's results were based on rigorous cavity arguments. So more or less in the spirit of Mizar's paper here. So I myself have written recently a paper together with Shuta Nakajima, Naiki-san, and Shanshi Su, which is based on a tap approach, which is not based on this cavity arguments. So our results are okay. It's still totally replica symmetric. But it's the most general results which exists nowadays about this replica symmetric results for this perceptron here. So. Yeah, just one remark. Because there were some recent papers, also rigorous papers here by Montanari and co-authors. If you're looking at the case which I have here, so just this situation. Now this is supposed. There is an exact critical point. For the alpha parameter. So and. I haven't written down how this critical point is exactly, but it's actually it corresponds in principle to this De Almeida-Saules situation in the Sherrington-Kirkpatrick model. And then the claim is that if alpha is smaller than this critical value, then it's replica symmetric here. So, but the critical point is also the critical point where afterwards. This number here appearing is 0 with high probability here. So now this is actually not proved, but there is a paper, quite recent paper by Ding and Sun, which are based on this tap approach also, which proves that the limit of this quantity is bigger than 0. That's a mathematically rigorous proof fact for alpha smaller is alpha critical here. So. Now for kappa, you see, in this sense, if you're having a kappa bigger than 0, there is no interesting replica symmetry breaking phase here. But actually, if kappa is negative, which is sometimes called the negative perceptron, there are recent bounds in a paper by Montanari. It's not yet published by Montanari, Song, and Zhao, but it's on the archive, showing that the replica symmetric situation cannot be correct for large enough alpha. So they are not getting a precise formula, but they're getting bounds which contradict the replica symmetric formula which exists in this case too. So that's a little bit a quick survey about this perceptron and the bipartite model. Now, what I want to do next, and that's a little bit repeating what Bernard Derrida had been telling you about mathematical proofs for the Parisi formula. So, rather quickly, I will explain how the mathematicians did prove that. So, some indications or some explanations were given by Bernard Derrida. And then to explain why. Part of actually an important part of it does not work for this perceptron and for the bipartite models, and what some of the ideas are, but they are still very vague, what mathematicians have to get around that. So. Yeah, okay, I have to feel, you see this, okay, about just okay. I never really worked in applications, but probably Marc Messard had been telling last week a bit about that. So for instance, the Hopfield model you can interpret as a special case of a bipartite model, not with two groups of ±1 spins, but with one group of ±1 spins and one group of real-valued spins. And then you're falling also in this type of difficulties we have just in the case of the bipartite I've explained here. And particularly Montanari has a lot of recent papers related to perceptron-type models in connection with machine learning things. So my impression is, okay, I'm not a specialist in that. So my impression is that for the real problems which are popping up in applications in machine learning, the models are still much too simple. But then one gets some intuition of what is going on in real applications by investigating, for instance, these perceptron-type models which are coming up in this paper by Montanari and co-authors. Yeah, another point actually, okay, where I'm a little bit proud of is that these tap-type equations, on which I will talk shortly if I have time in the end. In situations which resemble the tap equations which pop up in connection with this perceptron have become, I think, quite important in numerical analysis, because they are the fastest algorithms in some of the models for compressed sensing here. So that goes back to Bayati, Dave Donohoe, statistician from Stanford, and Montanari. And it's based on an algorithm for the Sherrington-Kirkpatrick originally, which is due to me. So I think the models really, from the point of view of applications, have really serious applications here. But I'm not going into details of that. So. Now, the main mathematical difficulty, if you are going to this, for instance, just to the bipartite model, is this miraculous replica symmetric breaking bound by Guerra does not work here. So it is not valid in the bipartite case, at least not for the simplest one I have explained here. So, and also not you cannot do it in the perceptron case. Now I will shortly explain that, but based on this Eisenman-Sim-Star scheme, which I think is mathematically the quickest way to explain it here. So now, and that's based on a cavity argument. So the key point here in this Eisenman-Sim-Star scheme is that you just compare the partition function of the Sherrington-Kirkpatrick model with n plus m spins with the one with n spins. You are looking at the quotient here. So now, you see this. What you are doing is always you're first taking m fixed and let n go to infinity. You can think of m equal 1 for the moment, but later we need also a bigger m here. So now and then the sigmas which correspond to the first n spins I call sigma, and then the newcomers I call tau. So to make a clear distinction here. So. Now, what you're writing down is you're just writing it in terms. Okay, the denominator I'm writing here in terms of the unnormalized Gibbs distributions for the Sherrington-Kirkpatrick model, but it's actually important that you are dividing here not by square root of n, but of course the right thing is you divide by square root of n plus m, and then you have these standard Gaussians. You are getting that. These are the Gibbs distribution. And then there's just the interaction with the newcomers. Now, in principle, this is given by this cavity variables. So y sigma I, which is just given you're summing over I, and then you're looking at the j's variables, at the Gaussian variables for j equal 1 up to okay. I have the typo, that should be j here. So sorry, no, not I. It should be j. So you're looking at that. So in principle, you should have here n plus m square root of n plus m, but it's a slight approximation, and you see immediately that you cannot forget it here, but you can forget it here. So, And then you have still the self-interaction among the newcomers, but if m is fixed and first n goes to infinity, that's also irrelevant. So that I have dropped out. Then in the denominator, of course, you would have this partition function for the Sherrington-Kirkpatrick at n, but you won't divide it by this, and then there is, okay, you just artificially, in principle, you should here square root of n, but then you correct it. You see, actually, you cannot forget about this correction, but you can just correct it in an artificial way by x of square root of m half with beta, of course, and then you have this kappa, which are also Gaussian random variables here. So in the outcome, what you're having here is you're having the inputs for this whole expression, which, okay, that is just, it's elementary to derive it. So in the case, you're just looking at these quotients for this Sherrington-Kirkpatrick. You're having then the Gibbs distributions for Sherrington-Kirkpatrick. Then you're having these cavity variables. And these are independent. You see also for different, of course, they are not independent for different sigmas, but as a group, they are independent for different j's here. And also these you are taking independent. And the cavity variables, they have correlations which are just given by this overlap, this Q, which is just the normalized inner product of two groups of spins. Here, you see, of course, they are not independent because you're having these non-vanishing correlations. And the kappa, you just do the computation. The right thing is for the Sherrington-Kirkpatrick, is just to take the Q square of this object here. Yeah. You see, the point is you are just taking this, the main expression is you're taking these three groups of random variables. Now, the key idea in this Eisenman-Sim start paper was that you replace these objects by a very abstract version of it here. So namely, instead of sigma n, you're taking an arbitrary countable set, so it can also be finite. And then you have random Gibbs weights, which I'm writing here as eta alpha. So alpha is in A now on this countable set. Okay, I assume here that the total sum of this eta alpha is finite. And then an abstract, possibly random overlap matrix, Q alpha alpha prime, which is just assumed to be symmetric and positive definite. Actually, one also assumes that Q alpha alpha is 1. And then one defines these cavity variables and the kappa exactly in the same way as above with these covariant structures. You see, you can express these covariant structures in terms of this abstract now overlap and the kappas also. You're just making the same assumption. Of course, it's no longer given in this way, but just given by this matrix, and then you write down this expression where you replace that here by all these abstract versions. But the taux are still plus minus 1. So you see the taux are still plus minus 1s, M, capital M plus minus 1 spins. So. Now, and then what you are writing is I'm writing GM of beta. In principle, you can also include, but I have kept h equal to 0. You can also include the h parameters. But okay, and you are just plugging in this abstract overlap structure here, and then you're looking at the right-hand side of the expression above. And okay, I divide by n, and then the expectation of all this object here. So you're writing that here. So is it clear what it is, what I have done? So I've just started with this cavity, the standard more or less cavity thing you're doing in Sherrington-Kirkpatrick, but then I'm replacing the SK part of length n by just something abstract, so very abstract, which is just given in this way here. So now, the miraculous property proved by Guerra, and in this for this abstract version, it's by this Eisenman-Sim star, is that if you are looking at 1 divided by m, expectation of logarithm of the partition function for the sk, it's smaller or equal to gm, beta, and r for any m and every abstract overlap structure. Yeah, so that's this key property proved by Guerra. So now the proof is actually not very difficult. So what, okay, I have not written down the proof. So what you are doing is that you are just interpolating between SK overlap structure with the abstract one by taking, say, square root of t times the Sherrington-Kirkpatrick one plus square root of 1 minus t times the abstract one. And then you're writing down the corresponding interpolated system, and you take the derivatives with respect to t, and then the derivative has the right side in order to get this inequality. So it's a miraculous property because it really works for any abstract overlap structure and for any capital M. Now, the similar structures can be derived for multi-particle models, so especially also for these bipartite models. So that was done later by Panchenko. I will mention that. And probably also for the perceptron, but it has not been done for the perceptron. But whereas bound will in general not be true. So that's the main shortcoming of this method. So if you're going to this bipartite model, then the bound will not be correct. So that's now you can think, yeah, it's just a technical point. So you had done this proof in a very simple way by doing this interpolation, this clever interpolation, but the computation is not very complicated. Maybe you should just do the interpolation more in a more sophisticated way, but it's actually the inequality is just not true. So. Now, what you ask next to is that you're plugging in this. No, I have looked at that now for an abstract overlap structure, but you can plug in a special one. And the special one is this real cascades. But okay, of course, because I have been a co-author in this paper, I explain it. It's more compact in terms of this coalition process here. Which was in the paper with Alain Snitman here. So in that case, you're just taking for this set A, capital A, which corresponds in the Sherrington-Kirkpatrick just to minus 1 to the power n. So and then I'm taking a parameter x, which is smaller than 1. In the end, you want to take x equal to 1. And then the Gibbs weights are just given by, okay, they are not normalized yet, so you're just taking as a Poisson point process on the positive real axis with this intensity measure t minus x minus 1 here. So it has as a consequence, x smaller than 1 has a consequence that you can sum these ones here. And then you can order them downwards. And now you can choose you can choose for this abstract overlap matrix Q. You're choosing them in a random way. You see, if you're looking at the Sherrington-Kirkpatrick, of course, then the overlap was determined deterministically. But in this case, you have to take it in a random way here. So this is Q's are defined in a random way. And it's quickest explained in terms of this correlation process. Now, this correlation process is a Markov process on the space of partitions on the natural numbers here. And you see the space of partitions of you just take the partitions into actually finite or actually in the end there are countably many. So you just divide n into subsets. So that's a partition. So and the space of partition you can easily make into a compact space here, a compact metric space here, and you define a Markov process on this compact space. And then what you just have to define is because it's in continuous time, you just have to characterize the conditional distribution. How if you are at time t in a certain situation, so in a certain partition, how are you proceeding in, say, infinitesimal time here? So now what you have to do is you first should look at restriction of this partition to a finite subset of the natural number here, so just 1 up to n. So of course, if you have a partition on the whole natural number, you just take the intersections and you're getting a partition of this set 1 up to n. Now assume that it consists of more than one set here, so that you have, say, capital N such sets, and you're looking at the partition of, again, of 1 up to n obtained by clumping one group of k sets of this restriction of lambda to these sets together here. So then in a time slot, in an infinitesimal time slot, then the process jumps with probability, so dt, so this infinitesimal time length, and divided by this quantity. So you see, it's an extremely simple object here. So you for instance, do oops, is there an eraser? Ah, it's here. Now, I think, for instance, you are having some points up to n, and then you have, say, 5 groups. Of course, they have not been successive, but the Druids are, say, by 5 groups. So n equals 5 up to n. And then you decide to clump just these 3 together. And then you have just and then, so you just have clumped exactly 3 together. Then the infinitesimal probability that you jump in this time to this situation is just given by 4, and then here 3 over 1. So we're just having that. So it's just that it's as simple as that. So. Now, what you are of course getting is okay, you're starting with at time 0 you're taking just a trivial partition into single points. And then you follow this. Actually, there is a little bit of mathematics to do because you have to extend it. That is just explained how we do it for n, but it's compatible for different n, and then you can define it easily on the full space of all partitions. And you are starting with a partition which is trivial in the sense that you are having just individual points here. So, and okay, that's in a well-defined object here. And now what you are taking is you're taking a non-increasing function f from r plus to 0, 1. And then I just call it the qij. So for this abstract overlap structure corresponding to real is just f of tau ij, where tau ij is a matching time of points ij under this correlation process. So it's as simple here. So then I have completely characterized this abstract overlap structure. And then it turns out that if you're computing this object here, but now with this real cascade, then first of all, it doesn't depend on m. You can easily compute it. And you still have to take the parameter x going up to 1. But then this is just given by the parity formula. So no. Where mu, the measure mu is the law of f of tau, where tau is this matching time of under the correlation of two points here, for instance 1, 2. So it's actually exponentially distributed. And then you're getting from this Eisenmann-Sim-Starr-bound, which is essentially following Guerra's argument, you're getting then really the Guerra bound, so the upper bound for the Sherrington-Kirkpatrick model here. So, but this, as remarked, this part that does not work for many other models here. So that's really special for Sherrington-Kirkpatrick. But it's generalized. It can be generalized to p-spin and also a number of other cases here. So the next thing is I started the quarter past. So okay. Yeah, the next thing is okay. I'm going quick now. Is this Gilanda also? Bernard Derrida has already shortly explained it. So these are these Gilanda-Guerra identities. Now, mathematically, there are some problems because these Gilanda-Guerra identities are not true exactly for the Sherrington-Kirkpatrick model. So you're having to do a little bit of a perturbation of the model. So for instance, you can randomize a little bit, for instance, the temperature parameter or doing something like that. So you have to do a little bit of a perturbation in order that the Gilanda-Guerra identities are correct. So, but what you can do is that you can take the perturbation in such a way that in the limit, so actually that the perturbation is decreasing if n gets large, in such a way that the free energy is not changed. So for computing the limiting free energy, it doesn't matter that you have to do this perturbation here. But mathematically, strictly speaking, the perturbation is necessary in order to get the Gilanda-Guerra identities. Now, the Gilanda-Guerra identities are, you're looking at, you see, okay, you're looking at the Gibbs measure here, and then you're taking just independent copies. But for fixed disorders, so for fixed omega, okay, for fixed J's, capital J's. Here, so you're taking independent copies, and then you're looking at these independent copies of this object, and then you're computing this matrix, which is given by the overlaps here of different copies here. Now, what the Gilanda-Guerra identity says that and that was first proved there were different setups where this was proved. But the Gilanda-Guerra's identity says that if you're letting n go to infinity, you're looking at the measure. You're taking n+1, small n+1 of these replicas, and then you're looking. For instance, you are interested in the law of this overlap of say the first one with the n+1 n plus first one, and you're taking the conditional distribution under this measure, given that you first have the full matrix up to n. So you see you're just taking this probability distribution, and then you are conditioned that you know all the overlaps up to small n. And then what turns out that the conditional distribution of the overlap of the first with the n+1 is that you are just choosing with probability 1 divided by n, just one of the overlaps of the first up to that here. So you see you're choosing with 1 divided by n, one of these overlaps on which you have conditioned here. So you see, and these are, of course, only n-1s. And you're taking probability 1 divided by n. So there is a probability 1 divided by n left. And then you are just choosing an independent copy under this law of this R12. So you can formulate it in this way. So it's equivalent to what Bernard Derrida has explained here. So now, and then there is this remarkable theorem by Panchenko, which is saying it's actually okay. It's very roughly stated because to formulate it properly, it's actually a lot of mathematical machinery to explain it properly. But essentially, it says that if you're having this Gilanda-Guerra identity and you're looking at the n equal to n go to infinity limit, then the overlap laws are the ones coming from the real cascades. Yeah, so that's I know that historically people first didn't believe it. So also Guerra didn't believe it for a long time, that it characterizes ultrametricity. So, and even, actually the next step is not very difficult. If you have proof that is ultrametric, it has to be a real cascade. So that's based on, that comes out quickly. But really the proof that you're getting the real, that you're getting ultrametricity out of the Quillander-Guerra identities had been really mathematically one of the absolutely fantastic steps in this whole development here. So now, with that, you're getting an alternative proof of Talagrand's result, namely you're getting the lower bound. So for instance, you're just looking at this quantity here, so expectation of log of Zn plus 1 sk divided by Zn. And then you are taking the lim-inf of that, and then the lim-inf of the partition function is bigger or equal to the lim-inf of just this quantity. And then, okay, there is still considerable technical work to do, but because you have this limiting ultrametricity, you can see that this, what you are evaluating here is given by an expression, a Parisi expression here. So, because you know that in the limit, in a certain sense, you have to formulate it precisely, which is not totally trivial also, but in the limit, you're ending up with the real cascades. And if you're plugging in the real cascades, you're getting the Parisi formula here. So. And therefore, you're getting that the lim-inf of this partition function is certainly bigger or equal to the infimum of the Parisi expressions, the infimum taken over all the measures here. So. And together with Guerra's upper bound, this proves the Parisi formula for Sherrington-Kirkpatrick here. So. Now, what Panchenko proved actually for the bipartite, and then this gives an indication how really the situation should be in the bipartite case, and I believe that it should also work with some efforts also for the more general perceptron case, is that if you're just looking, for instance, at the bipartite case and also on multi-species, more complicated multi-species model, he proves that actually you have an Eisenmann-Sim-Star kind of scheme, and then there is a bipartite Parisi expression here. So because, for instance, you have two groups of spins, and then for each group you are taking a mu1 and mu2, and you can write down a Parisi expression for this pair of mu1, mu2. There's actually considerable work to do in order to prove it, because one of the key things he has to prove, Panchenko, is that if you're looking at, you see you have two groups of spins, and in principle you can have a cascade structure for the first group, a cascade structure for the second group, but in principle you could have something much more complicated here. So where the two groups are somehow mingled together in a more complicated way, but this is not happening, so he proves that. You're just having one cascade structure for the first, one cascade structure for the second, and they are coupled together, but they are coupled together in deterministic ways. So that is a non-trivial fact he proved here. So, and then he proves that you have a lower bound here, so you have the same lower bound. So, and that works for arbitrary. Particularly for the bipartite model I have written down here, you get this lower bound, but nobody believes that this lower bound is correct for the bipartite case here. So I think it's even proved that it is not correct here. So now, actually, for some of the multi-species model, there is a Guerra upper bound. So you see in the beginning I had explained that they are actually, if you are having also interactions inside the groups, and you would have a matrix, so of temperature parameters. So one temperature parameter for the first group, one temperature parameter for the second group, and a third temperature parameter for the interaction. And if this matrix is positive definite, then you also have Guerra's upper bound. That was proved in a paper by Barra, Contucci, Mencion, and Tantari some years ago here. So. And in that case, you are having the full Parisi formula also in this case, here. So now, but you see, if for the strict bipartite case, you're having temperature parameter 0 in the diagonal, and then, of course, the matrix is not positive definite. Here, so. Now, although it is not stated in Panchenko's paper, I think his argument should essentially prove, it might still be technically a bit complicated, is that if you're looking at the partition function for large n, for this bipartite case, you should get just this partition formula for some mu1, mu2. But the question is, what should mu1, mu2 be? Do you have a variational formula? That's a totally open question. Yes, namely to have a variational formula. But the point is, and Guerra was propagating that you can, of course, also look at the high temperature region, and then you have a replica symmetric situation. And in that case, the mu1 is a delta function at Q1, and mu2 is a delta function at Q2, and you can write down the expression. And then actually for Q1, Q2, you can have a fixed point equation. You can write it down. But what was in a paper by, I have cited it somewhere. So I think earlier by Barra, Guerra, and Genovese, is that if you're having then this Q1 and Q2, you're having, for the limit, a minimax expression. So you're taking the minimum over Q1 of the maximum over Q2. And I think Guerra was, without having a proof, was advertising that something like that should be the general situation. Yes, but that is mathematically a totally open question. Yes, I really want to talk about this shortly, 5 minutes, about this Hamilton-Jacobi approach. Now, this is a quite new development by Jean-Christophe Murat. Now, the idea goes actually, he was not the first having this idea. The idea goes also back to Guerra, Barra, Genovese, and others. Now, it's best to explain it in the trivial Curie-Weiss model here. So you see, which is, of course, a non-random object here. So the most basic mean field object where you are having, the Hamiltonian given by this double sum, and there's no randomness here, so just 1 divided by n, which you just can write as minus n times, and then the arithmetic mean. So I'm writing this arithmetic mean as sigma n bar. So we're just having this arithmetic mean, and this just square it. And then the free energy is, the limiting free energy is just given. Of course, this is, you can just write it down what it is by Stirling's formula. Of course, that's more or less a trivial computation, how to evaluate that here. So now, you see, but the model has a phase transition. I think if here at beta equal 2, if you write it in this way here, so you have, so probably everybody knows this Curie-Weiss model here. So now the key idea, the starting point is if you differentiate this Fn with respect to beta, you are just getting here the Gibbs expectation of the square of that. Of course, this is just coming out from this computation. Now that is not very useful to observe, but the key idea is that you should not look at this model here without an external field. So you're just taking this beta as before here, so that's the same as before, and then you have an external field with h here. So then you have more possibilities to differentiate. You can differentiate with respect to beta, and you can differentiate with respect to h here. So now if you do the computations, so what you're getting is that if you differentiate Fn with respect to beta minus the square of the differentiation with respect to h, then this is exactly equal, that's an exact equation, it's the second derivative with respect to h divided by n. And therefore, you somehow expect maybe that if n goes to infinity, this right-hand side goes to 0, and you expect that this object here, the limiting object, is satisfying just this Hamilton-Jacobi equation with the boundary condition at beta equal to 0, which of course you can exactly compute, which is logarithmus cosinus hyperbolicus h. So you're just looking at solutions of this equation, and you're hoping that f is this solution. Now the point is that there is no unique solution of this, even this simple equation here. Okay, you have to be a little bit careful how to define a solution. But the correct solution you get by the so-called viscosity solution. You see, this is and then actually you can prove that you're getting the correct expression here. So the correct expression is the viscosity solution, and you can prove that. The viscosity solution is that instead of writing here 0 on the right-hand side, you are taking again a Laplacian here you smooth it out. There's diffusion terms here. And then you, with a small parameter epsilon in front, and then it has a unique solution, and then you let epsilon go to 0, and you're getting the correct solution. That's a complicated proof of something which is trivial by the Stirling's formula. So that's for the Curie-Weiss model. It's of course not the way to prove it. But what Murat has propagated is that you can do that also for spin glass models here. And his success, okay, with some success, so one has to say, actually considerable success, he could do that. Now, instead of this enhancement just by an external field, you are having to do an enhancement in an infinite-dimensional way, namely essentially with relatively complicated quantities which are directly coming from the Ruel cascades. Yeah, but they're involving also all these measures. You see, these Ruel cascades have as a parameter these measures on the unit interval here. And in a paper which appeared in 2.1, he was. Okay, he couldn't, he did it for the bipartite case here, exactly for the bipartite case. And he could not get really the limiting expression. But what he could do is he got an upper bound. Okay, it's of the lim sup, of course he doesn't know that the limit exists here. So of this finite n free energy, in terms of a unique viscosity solution of an infinite-dimensional equation like that. So instead of having just a derivative with respect to h, he has to take second derivative with respect to the square of the derivative with respect to h. He has, in that case, to take derivatives with respect to a mu1 and a derivative with respect to a mu2. So an infinite-dimensional derivative, which actually have to be defined in a somewhat complicated way. It's not just Fréchet differentiability or something like that. So it's getting technically extremely complicated, but he got the rigorous upper bound, which is remarkable because Guerra's upper bound here completely fails in this setup. But for the moment, okay, he was giving lectures in Zurich, so at least in December he was not yet able to evaluate the limit, but he conjectures that this viscosity solution gives the correct answer here. So now the next problem is, of course, if this viscosity solution has a variational representation. Now, these Hamilton-Jacobi equations often have variational representations of the solutions, as in the Parisi expression. But in that case, it's actually much more complicated because for that you have to assume some convexity assumption, which are not correct in that case. Yeah. So if even if he's right that this viscosity solution gives the correct answer, it's not clear if you have a nice variational representation here. So okay. No, I'm already over time. I had prepared something about our approach with our TAP approach to evaluate the free energy, which for the moment only works for in the replica symmetric situation, but I think the idea is maybe okay. I still hope that in the end one could do something also in the replica symmetry breaking situation, but for the moment it's just restricted to that. But there are a number of papers which were doing it. Was first introduced here, and then actually there was a recent paper by Brennecke and H.T. Yao. So also that was just for the Sherrington-Kirkpatrick, and then there is this recent paper using the method also for the perceptron, and this is the best result on the perceptron just in the replica symmetric situation, mathematically rigorous results. But okay, I'm already a bit over time, so I stop here. So thank you very much.